This is the internal combustion engine week 1 presentation for ME 4056 section A2 group 3. The members are Dylan Phelps, Natasha Vermouth, Andrew Imig, and Yishao Hu. Generative Energy Systems Incorporated has created a modular internal combustion engine and has tasked the team with determining system parameters and control for the new system. To determine the system parameters and control, the team will use deterministic equations, analytical models, and experimental data collected using the lab setup described in the following slide. The goal of the experiment is to optimize control of the system for the best power generation.
The Elvis board connects to the analog sinusoidal encoder and the force transducer, which are attached to the IC engine. This serves as the data acquisition system for week 1 of the experiment, determining the voltage applied to the motor and receiving the data from the 2 sensors. The data is then displayed in LabVIEW. Using Vinca calipers, critical dimensions of the engine are determined. Calibration is done by recording the response of the force transducer as weight is added to the moment arm, which is attached to the motor. Calibration will be done each week for the following experiments. The motor runs at 0.3, 0.6, and 0.9 volts with 4 flywheel weights attached. Data concerning the force transducer voltage, encoder, and electric cam state is collected. The same process is done with only 1 flywheel weight attached. And those are pictures of the encoder, force transducer, and then the engine as a whole. Results. So this is the calibration plot. You can see we got a gain of 1.3951 volts and a offset of 1.081. So to obtain the work done by the motor, the steady state portion of the torque versus angular position data must be numerically integrated, which can be shown in this table for each of the runs at low speed, medium speed, high speed, and with the different masses attached. The torque due to friction is determined by averaging the steady state portion of the torque data. These friction torque values are shown in the table. The frictional torque increases in magnitude as the RPM increases.
The theoretical moment of inertia for 1 mass and 4 mass can be seen in the top table. The flywheel moment of inertia can be seen in the bottom table for low speed, medium speed, and high speed for both 1 mass and 4 mass. There is certainly a bit of discrepancy between theoretical and experimental that comes with data collection. This discrepancy likely comes from uncertainty of the voltage reading when calculating torque values. Even though we are calculating average torque values, it doesn't completely eliminate the other primary source of error, which is noise. That being said, these values are fairly accurate and they're precise. It can be seen that the moment of inertia values are more so dependent on mass rather than RPM. In an ideal and perfect experiment, the moment of inertia would be the same for 1 mass at any speed and for 4 mass at any speed. Removing the flywheels causes the engine to accelerate a lot sooner and reach steady state a lot sooner, as heavier objects have a slower acceleration rate. Top speed will be the same regardless of mass. This can be visualized by observing these graphs side by side. The 1 mass plate will reach steady state a lot sooner in time and position. It reaches steady state at a position of about 100 radians sooner than the 4 mass plate. The same applies for medium speed, as the 1 mass plate will reach steady state at about 300 radians sooner than the 4 mass plate. And the same applies for high speed. The 1 mass plate will reach steady state at about 200 radians sooner than the 4 mass plate.
So now, based on all the data we collected in the previous experiment, we would be able to construct a theoretical model, which is a theoretical model for energy system comply with kinetic energy, work of the motor, work of the friction, work of the piston, and work of the air. However, for week 1, since we don't have the headings, work of piston could be negligible, and we don't have work of air. That's why we only have work of motor and work of friction on the right-hand side of the equation. Moreover, we would be able to derive the moment of inertia, just like as Natasha mentioned, and we will be able to directly get the angular velocity from the data set we have. The same applied to the work of motor as well. Since we don't have work of air and work of piston, the behavior of this energy system, instead of a 4-stroke, it's more like a 2-stroke behavior. So we could see that the data collected for work of motor are very similar for the first 2 strokes and the second 2 strokes, which is the compression and the power. They are very similar, and exhaust and intake, they are very similar. That's why we only have 2 strokes system only for week 1. In week 2, we would incorporate work of air, which would make it more like a complete model. And the 2 strokes, as you could see from the table, the values we calculated for each of the components, when you add them up, they are not directly equal to 0. This is because, firstly, we only done 1 experiment, so the value we get may not be very accurate. There are a lot of uncertainties involved in this experiment. Moreover, because of the noise, the data we have fluctuate, and which might influence the final results. The same would be applied for 4 mass. The only difference between 4 mass and 1 mass is that the initial kinetic energy and the final kinetic energy are higher compared with 1 mass plate. This is because the mass is higher. Since it has a higher moment of inertia, the initial kinetic energy and final kinetic energy is also higher. The same would apply to the work of motor because we have a higher torque of friction. Now, in conclusion, the friction increases as we have a higher speed, which also increases the work of the system. The moment of inertia is primarily mass dependent and also depends on the geometry. That's why the change of RPMs would not increase or decrease the moment of inertia we have. However, we do get different results compared with theoretical value. This is because we have like a really large noise, and also uncertainties would take place. However, noise would have more impact on low speed and low masses, as you could see from the previous graphs. This is because if, the higher noise values would change and fluctuate the data more than we have for like a higher value results. That's why in the end, we will be able to construct a 2-stroke theoretical model based on our previous experiment.
For week 2, the data collection includes measuring system characteristics while in steady state operation. In this week, we'll be testing the system with the motor driving the engine. We'll calculate the work due to air and the work due to piston, and then put it in the modeling equation and compare that to experimental data. With all this, we will factor in uncertainties and make conclusions based on that. In week 3, analysis will be done on the same system in simulated combustion, which is where the engine will be configured to drive the motor. With a trial and error process, we will find an optimized max power air injection angle range for the system, for the motor. Then these experimental results will be compared to the modeling equations by stroke, and then again, uncertainty calculations will give us a certain set of conclusions and confidence in our results. So that's the end of our presentation.